Hi everyone. Here are a couple of examples getting started with function notation. So we just want to make sure we're comfortable with the notation for this section. Okay, so first one, I have a function that's described with words, and we want to make sure that we can make some sense of some statements given in function notation. All right, so our function, b equals n of t. So when I look at this, make sure you're recognizing that t is your input variable. We're inputting t values. B is your output variable. We're outputting b values. And n is the name of the function that pairs b values with t values. So function n pairs b's and t's. And this represents the number of birds in thousands. So B is the number of birds in thousands, migrating through Washington T years after 1990. So both of these variables have a little bit of a particular definition. You want to make sure you're really careful with that. We need to make sure that anytime we see a B value, we recognize that that is thousands of birds, not just birds. And anytime we see a T value, that's the number of years after 1990. All right, so first statement here, we want to explain the meaning of n of 7 equals 9.2 using everyday language. And this everyday language thing actually is really important to me. It's great if we can sort out the meaning of that, but part of the job of mathematics is to be able to then take something like that and explain it in a nice, clear way where somebody who is not taking pre-calculus could understand what the statement means. So n of 7 equals 9.2. 7 is our input values, and inputs we've already decided are t's. So this is 7 years after 1990. And the 9.2 is our output value. We've decided that our output variable b is giving us thousands of birds. So this is giving me a basic understanding. 7 years after 1990, there's 9.2 thousand birds migrating through Washington. I think I can do a lot better if I'm trying to make that everyday language. I don't know about you, but I think 7 years after 1990 is sort of an awkward way to say it. And I definitely think 9.2 thousand birds is a strange thing to say. I wouldn't mind 9.2 million or billion, but I don't think it's normal for people to say 9.2 thousand. So if I want to nicely explain this with everyday language, I would simplify it as much as possible and say in 1997, 9,200 birds were migrating through Washington. I do not need you to word this exactly as I word it. This is definitely open for you to give whatever wording you see fit within reason. Again, I am going to look for it to be simplified. So if you do things like 7 years after 1990 or 9.2 thousand, I would say, yes, it's really clear to me what the answer is, but I don't think you quite simplified it. Just so that you get what I'm thinking when I look at that. If you were solving an equation and you stopped at x plus 2 equals 7, it's really clear to me what the answer is, but that doesn't mean you're done solving. You need to take the last step, subtract 2 from both sides, and tell me that x equals 5. So please change your wording from 7 years after 1990 to in 1997, and from 9.2 thousand birds to 9,200 birds. So I really do want you to do your best for everyday language on this. Okay, this one has one more part. If n of 9 is equal to 6.1, find the average rate of change of n from t equals 7 to t equals 9 and explain its meaning using everyday language. Okay, so we are supposed to calculate an average rate of change, which means we need 2 points. One of our points was given in part A. So if I know that n of 7 equals 9.2, that means I have a 0.7, 9.2. And then in this new part, we're given another point, n of 9 equals 6.1. So we have the 0.9, 6.1. if you remember your average rate of change formula, we are supposed to take change in y over change in x, so it's slope, and you get to choose which is your first and which is your second point. So I'm going to say 9.2 minus 6.1 is my change in y. So I've chosen order here. If I'm doing 9.2 minus a 6.1, I just need to make sure that I'm using the correct order for the corresponding input values. So 7 was the input that goes with 9.2, and 9 was the input that goes with 6.1. Okay, so we need 9.2 minus 6.1, 3.1 over negative 2, which is going to give us 1.55, negative 1.55. Okay, so this is my average rate of change. I'm also supposed to explain what that means using everyday language. These can be a little bit awkward to explain, but just remember that it's a slope. So slopes are always fractions, change in y over change in x. And in fact, if you wanted to, you could use this 3.1 over negative 2, but I'll go ahead and stick with my negative 1.55. And remember that this is saying the change in our output variable is negative 1.55, so that's change in b. This delta right here is something that's really common for people in math to use for change. And the 1 is a change in t. So this is for every 1 year, the number of birds migrating through Washington is expected to decrease by 1.55 thousand. So again, making that sound a little bit better, 1,550. It is really good to identify that this is just an average. This is not perfect, but if we average over the 2 years, that's the decrease we're getting, and to specify what years we're talking about. So I would say if we want to get all of the information in this statement, it would be something like this. Between 1997 and 1999, the number of birds migrating through Washington decreased by 1,550 per year on average. I would say that's a really complete interpretation of the average rate of change. So when I'm looking at those, this is a little bit of a picky one. You want to make sure that you have given the interval for which the average rate of change is valid, that you've clearly described the change in your output variable, change in your input variable part, so decreased by 1,550 every 1 year. Those are really important. And you want to make sure that you mention that it is in fact an average. So be really careful about those. That's one of our messier interpretations. One more example in this video. This one doesn't have an application, but it's just looking at functions represented by tables. So we're saving up formulas, but we're trying to get a look today at functions described by words, tables, and graphs. And here we actually get to talk a little bit about whether or not this table represents a function. So I have 2 different tables. Let's just focus on this first one. We would like to decide if this first one is in fact a function. So I'm going to let you look for just a second and then we'll talk about it. Okay, so pause if you're not ready to hear yet. A lot of people are bothered by the fact that we have this 1, 2, 1, 2, 1, 2 thing happening and worry that that means it's not a function. Okay, so let's walk through this step by step and make sure we're really clear. First thing is, if we are looking at this as a potential function, we should be able to identify where we would look for inputs and where we would look for outputs. So if this is f of x, x will be our inputs, which means this top row is the domain of our function, assuming it actually is a function. And the bottom row The f of x's are our outputs. So again, if this is actually a function, the bottom row tells us what is in the domain of our function. Okay, so remember the rule for a function is the exactly one rule. So if I pick an input, say -1, I want to check and see if I get exactly one output. So when I plug in -1, the table tells me that I get out a 1, and I don't see any other values, so that wasn't exactly 1. If I plug in -1, I get exactly one output, +1. If I plug in 0, I get exactly one output, 2. If I plug in 1, I get exactly one output, 1, and so on. So this is a function. Again, what I would be looking for is an input value that does not have an output or an input value that has more than one output. Either of those would mean this is not a function, but this one looks great. So to get our function notation in the mix here, if I'm trying to find f of 1, I just walk through how to get input-output pairs. This is saying 1 is my input, so I'm going to go to the input rows, I'm going to pick out the 1 in the input row, and I'm going to say I should get exactly one output, and it turns out that that exactly one output is also a 1, so sort of boring, but really important to recognize that this is the input 1 and this is the output 1. I am also asked to find f of 6. So this is just to get across the point about tables. Unless it says otherwise in a problem, if I give you a table and say the table represents your function, I mean that's the entire function. Sometimes it'll state very clearly that you're only looking at some values of the function, and that's fine, but you want to think about that carefully. So here, I'm not expecting you to extend out the pattern and say f of 5 would be 1 and f of 6 would be 2. I'm expecting you to say 6 is not one of the possible inputs of this function, so 6 is not in the domain of this function, which means the function is undefined for the input of 6. And that wording is important. There are some alternatives that I would take. A does not exist. We tend to use that more for calculus, but I would be fine with it. The value for function f at input 6 does not exist. I would be fine if you said 6 is not in the domain of the function. I think that's a really clear way to state what the problem is. But something along those lines is important. And we'll get at kind of a different question that confuses people, that people mix up with that one, so that you understand why I'm making such a big deal about the vocab there. All right, you should also be able to solve. So basically what I've done up above is I've given you an input and asked you for an output. I should also be able to give you an output, for example, f of x equals 1, and you should be able to tell me any inputs that go with that. So now when I go looking for the 1, it is not in the inputs row, it's in the outputs row, and it actually appears 3 times in the output row, which means I'm going to have more than one answer. It looks like f of x will equal 1 if x is equal to -1, 1, or 3. So I want to make sure we're really clear on the fact that it is completely acceptable for us to have 3 different inputs with the same output. That doesn't violate our exactly one rule. Our exactly one rule says if we choose a single input, we can only get one output. It doesn't say anything about choosing a single output and getting unique inputs. There is a rule that talks about that, and we'll come across it later in the quarter. It's called one-to-one functions. One-to-one functions not only have exactly one output for every input, but there's exactly one input for every output. So all input-output pairs are unique. You're never going to see an input repeated or an output repeated in 2 different pairs. So always look for all solutions. There can be more than one. Just to finish this one off, if f of x is equal to 6, and we're supposed to be looking for all possible inputs, we'd again go to the output row and say, okay, when do I get an output of 6? And the answer is never. So this is similar to when I asked you for f of 6, but it's not the same type of equation, which means it doesn't quite get the same answer. Up above, I was saying, what output will function f give you if you plug in a 6? And you're trying to express to me that there is no output defined for an input of 6. That's why wording like undefined or does not exist work up above. Here, I'm actually asking you to solve an equation. This is a statement that's true or false depending on what x values you pick. the output of my function is equal to 6, depending on what x is. That may or may not be true. If you're solving an equation and you find that there is no solution, that's how you should word it. This is a no solution. So it should be really clear just looking at the original statement of the question. Is the question just asking you to plug something into a function and find an output, or is it asking you to solve an equation? Only when it's asking you to solve an equation should you say no solution. Okay, one other table to look at, and then we'll be done here. Same sort of question as up above. So let's start with all possible inputs are in the top row and all possible outputs are in the bottom row. And again, I can tell just because of the way the table is labeled. So you'll get tables that are oriented vertically and horizontally. Inputs can be first or second, and you should always be able to spot that just by looking at the labels on the rows or columns. So first question we should be asking ourselves is, does this table in fact represent a function? So pause if you want a second to look at this. Otherwise, I would say, just like before, we're trying to make sure this passes the exactly one rule. So if we go, what is f of 1? We should get exactly one answer. And if I look at this table and I plug in a 1, I get back 0. That's great, but I also get back 3. So this table does not represent a function because the input 1 gets associated with 2 different outputs, 0 and 3. So not a function. Okay, that's it for this video. Thanks.